see how we got. So we won't watch the whole thing. I think it's about 26 minutes, but you kind of get an idea of what's out there.
Within 1 second is described as the frequency of the wave. One wave or cycle 1 second is described as the frequency of the wave.
There's video somewhere here.
One wave long EM cycles, such as radio waves, have the lowest frequency and carry long EM waves. Such adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum.
I knew there's a reason I don't show videos.
As you sit watching TV, not only are there visible light waves from the TV,
because nobody listens to them.
TV striking your eyes, but also radio waves transmitting from a nearby station.
Yeah, I don't know if you caught what I was trying to say after class started, but I'm not going to show the whole thing.
Everywhere you go, it is odorless and tasteless. Yet you use it and depend on it every hour of every day. Without it, the world you know could not exist.
God.
What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves, for longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
So that was just kind of a summary, kind of get you remembering electromagnetic spectrum, what we're talking about. So I brought, no, I didn't bring candy. Nice try. I brought, to try to kind of show you this idea of your sunglasses. How many people, when they get their sunglasses, they make sure that they are polarized? Yeah, you should. And it kind of goes to the fact that actually radiation has this sort of directionality to it. And so, kind of shown here, it's got the particulate we call photons, and it's also got kind of a directional part we call waves. So I snagged a couple of figures from the internet trying to sell you polarized sunglasses. And I also brought, kind of to show you what when you buy a pair of sunglasses, okay, this is what you're buying, right? So here's the deal. Your sunglasses are set up to become like picket fences, kind of like you see here, kind of a picket fence, okay? So even though this is light from everywhere, only a certain amount can get through. Does that make sense? So of course it's diminished. Its amount of light is diminished. So that's good. This is what your sunglasses are like. But it's directionally diminished. So you've heard of glare and that sort of thing. The thing about glare is it is totally random with regard to direction. So what your sunglasses do really well is that if there's glare coming your way, it's like, okay, I'll only take a sliver of that. So, I mean, you can see the object, obviously, but you don't get all the miscellaneous directional stuff. But here's the deal, and this is kind of shown here. If you take your pair of sunglasses, and I don't know how expensive they are, but if you break them, okay, you break your sunglasses, and you take them and you take the picket fences going up like this, take one of them and turn the picket fence the other way, actually sideways. If you turn the picket fence like this, you're like, hey, you basically have gone 180 and they're both going the same direction. But if you take the picket fence and go sideways, okay, what you've done basically is you have at right angles, said that you're going to not allow any light to go through. So again, you can do this with your own sunglasses. I think it might show me to do this. So, okay. I know. Cool. If you ever tried to look at your tablet with sunglasses, sometimes you're like, I cannot see my tablet with these sunglasses. Well, it could be that it's called polarized. Okay, if you basically said, I want only this light coming this direction, you've polarized the light. And it's possible that your tablet is sending out a certain polarization of light, and your glasses are just kind of going opposite of that. And that's happened to me before. It happens with your film. Sometimes it had to be a special film, but like on your windows, they can be polarized. Cool. Well, there you go. So on with the new slide. Some of you guys heard me say that, yes, we'll be in chapter 5 again on Wednesday. There ain't no way we're getting through chapter 5. It's a long chapter. Chapter 5 kind of reminds me of chapter 4, and it's kind of got, chapter 4 wasn't that long, but chapter 4 was kind of steeped with some of those, gravity and forces and everything. This we've got to kind of hit, we already hit the different types of electromagnetic radiations. And I like what that video from NASA said, because it's like this room is filled with waves that we don't know. Okay, we're glad we don't know them, actually. Okay, it'd be kind of confusing. So when radiation, and I know this says light, but if you go ahead and change this up here to any form of EM energy or EM radiation, okay, when those cousins, including light, hits matter, and we talked about atoms, okay, on Friday, when that energy hits atoms, it can do one of an assortment of things. Okay, those atoms can absorb that energy. Those atoms can allow that energy to go through. That's called transmission. Or those atoms can go ahead and interact with that energy and send it. Okay, sending it can be random. We call scattered. Okay, or it can be like a mirror. If you look at a mirror, you know what direction the light's going to return in. So this is important to astronomy to kind of understand these things. All right. So a few things here. You see people in two different positions looking at the same movie. Okay. Of course, we see a movie in this old kind of projection sort of scenario, because light was sent, little photons of different colors were sent from the projector to the white screen. It's probably like this, right? And since this isn't a mirror, but it's kind of basically a way for light to scatter back. So you guys are seeing this screen like they're seeing that screen, right? At all of your directions. So if we compare light being scattered versus light being reflected, of course, reflected, you think of a mirror. The thing about reflection is not everybody in the room, for instance, would be privy to the same reflection. You got an angle thing going on. Okay, scattering is random. Reflection is just only in one direction. But it depends upon the energy, in this case light, and the atoms. In this case a mirror, in this case over here, the projector screen. Okay, so those things depend. Put another way, do you think, what if a projector were spitting out gamma rays? It'd sterilize everybody in the room, probably. But do you think that screen would reflect those gamma rays? Gamma rays are, honestly, when we're developing telescopes, gamma rays are hard to concentrate because they go through everything. Okay, so it's just another cousin that doesn't interact with matter the same way. So I like the video we saw. Remember the green leaf just a minute ago? That's one of the things I want to talk about too. We said just kind of that narrow cousin, that narrow band of energy we call visible light, okay, has a certain range of wavelengths. And here's the deal. We count on visible light. It's the one that our eyes are sensitive to. I always think it would be interesting to think what it would be like if our eyes developed a sensitivity to other wavelengths, long wavelengths or shorter wavelengths. But the reason you see something, anything, is because that is the color that is reflecting. Okay? Just like the reason you see a green leaf is because that's the color that's reflecting. Everything else is absorbed. So I have an example here. I think this is a figure from your textbook. So odds are that living where we live, we may not have oceans, but we have snow. So if you go skiing, honestly, you're probably going to want to wear your sunglasses, okay, being exposed to all that snow, and maybe even sunblock. Because what that snow does is basically it takes white light from the sun, and notice nothing is absorbed. Okay? It's all reflected back again. And here's the deal. If you want to get white light, what you do is you take all the colors of the rainbow. And I think that's what Newton saw. So white light equals Roy G. Biv mixed up. Mixed. Okay? So here we see Roy G. Biv coming from the sun, Roy G. Biv hitting the whites or anything that's white, and Roy G. Biv coming back up. Okay. If we compare that to the tree, which is green, okay, quite clever. Notice that instead of Roy G. Biv, it's Roy Biv. Roy Biv is absorbed, green is reflected. So, what is black then? If something appears black, what does that mean? Do you ever wear a black shirt? Well, I know you probably do, but what happens if you wear a black shirt into the sun? It absorbs everything, exactly. Black absorbs everything. Okay, and that means absorbs Roy G. Biv. White, white light, or something white will actually reflect Roy G. Biv. And it will absorb nothing. Exactly. So just have some kind of more examples here. There's a guy in here, and notice that he can see, and I think it's interesting that the only reason you can ever see anything is because light has to scatter off of that thing. I know it's a small thing. But, you know, if you go into a dark room where there's no light source, you're not going to see anything, right? Yeah. So it's light scattering off the object for you to see it. And specifically, the color you see it is the light, the component of the light that scatters off of it. Okay. So, yes?
I read I watched this video about this guy, and he was talking about if we see colors the same. Like if her and I are like looking at your sweater, if we see the pink and the black the same
That's
color.
an interesting question.
So
She's saying if we all see the same color, like you can say I see pink, but what does that mean to you?
Are we seeing the exact same color?
Yeah, and what did he conclude anything?
He basically said that it's really hard to tell because it's really hard to describe a color. I mean, it's easy to describe one, but down to the exact pinpoint between two people.
Yep. Because like it's a specific wavelength, but you associate it, I mean, you've always seen it a certain way. I agree. I think that's an interesting thing.
I just want to know what your take on that is.
I just,
Since we're talking.
yeah. I think my take on it is I agree. I don't think that you can say we see yellow the same. Maybe that must be, or could be why some people hate yellow and some people love yellow. You know?
Yeah.
Like you're seeing it differently. I agree. It's very interesting. Okay, so Friday's lecture, we talked about an atom. Okay, and so I'm hoping that you kind of remember the little BB, and that was the center of an atom. And then this is electrons, okay? So we're switching our gear to just to kind of focus on electrons here. So the thing about electrons is that electrons can, sometimes they get a little bit of energy from the outside, and I usually kind of put my hand up like this to kind of show that they get more energy, okay? And then sometimes that electron can say, oh, I'm done with this energy, and it will go back to being a kind of a couch potato. Okay, so there are electrons outside the nucleus, and they can have different amounts of energy. Fireworks, okay? The thing about fireworks is that they take the metals, certain elements, okay, and they inject those atoms with a certain amount of energy. Okay, the electrons get excited, okay, because of the energy from the firework, and then when they fall back down, we get those colors. The thing is, they fall down just a certain distance or a certain energy, and that is characteristic of a certain color. So that's kind of how that goes.
So how exactly do they get the pattern in the fireworks?
I don't know how they get the pattern in the fireworks. It has to do with packing, I guess, and kind of delayed, and the fireworks, how do they kind of get the different...
I've always wondered that, how they get the specific pattern.
It is cool. Oops, I wanted to show you this flame test, though. I thought this guy did a good job.
Welcome home, buddy.
You and me, we were made for love. A lifetime is not long enough to show you what you mean to me.
The flame test. blue color that you're seeing immediately is going to be methanol burning. As the salt dissolves, you should see the various metals glowing their appropriate colors. Potassium chloride, actually let's start over here with the lithium chloride. Lithium chloride is pink. Strontium chloride should go to a nice orange color as it dissolves. Sodium chloride is that nice yellow. Copper chloride is green. And potassium chloride, you're getting a violet. Okay, you want to ignore that orangish tone that you see. The whole reason why these 5 different metals give off 5 different colors is because the metal, as the methanol burns, as the methanol burns, the metal is gaining energy. The outside of the metal has electrons on it, and that's what's actually gaining the energy. So the electrons jump in energy level. As they fall back down to their ground state, what comes up must come down, so those electrons must go back to their normal state. They have to give off that energy that they gained. They can't destroy the energy. So they give off the energy in discrete packets, very specially sized packets that we call photons. These photons right now currently are visible in visible light spectrum. Pink for lithium, orange for strontium, yellow for sodium, green for copper, and again, purple for potassium. The reason for the different colors is due to the different amounts of distance that the electrons fall as they go back to the ground state. Smaller distances falling mean a smaller energy light, such as the pink light of lithium. Larger distances, such as the purple light being put off by the potassium, are due to larger falls to the ground state. So the reason why these 5 different metals give off 5 different colors of light is because they have different electron configurations. And their electrons have the possibility of falling from different levels to different levels.
So related to astronomy, we can't like take part of a star and burn that. You know, we can't do that experiment. But what we can do is look very closely at energies that are being emitted from that region of space. And based upon those energies, based upon those colors, okay, we can say, I know what element's there. It's like DNA leaves a fingerprint. So these, what we call these transitions, leave a fingerprint. So, let's see. I like what he kind of alluded to, said in as much that there might be energies being released in not just the pink and the yellow and the orange. There could also be energies being released in the other cousins that we aren't privy to see. Okay, so we can kind of get that information. So kind of related to that, we're going to talk about 3 different kind of types of spectra. Continuous spectra, emission line spectra, and absorption spectra. And kind of keep in mind the idea that the electrons can be excited and electrons can fall back down. Okay, so it's all about the electrons. And they have a certain pattern depending upon what element they are. So this continuous spectra, emission line spectra, and absorption spectra are kind of summarized into Kirchhoff's 3 laws. Oh my gosh, there's 3 laws again. What do you think? Okay. So starting with Kirchhoff's first law, or continuous spectra. The word continuous means kind of like non-segmented, and that's kind of what we have with a continuous spectrum. Okay, it's Kirchhoff's first law. Basically, you have pure no interruptions. Okay, no interruptions. You have the Roy G. Biv, no interruptions. The next 2, though, you have interruptions that are due to the presence of a gas, presence of a metal. Okay, I guess either way. The metal could be in a gas, or the metal could be in the solid state. But emission line spectra are basically, when we saw the flame test a minute ago, we could use the word emit. We could say that light was being emitted from those flames. So that's what's being described here. He said how he had methanol there to kind of go ahead and burn. And just like in our fireworks, that went ahead and excited electrons around those different metals. Okay, and we saw them. That wasn't the part we saw. We saw the part when the electrons fell back down. Light was emitted in a particular color based upon what metal it was. By the way, I am totally not that brave to deal with those metals. Sodium metal in and of itself is like just highly reactive with water, and I just would not feel comfortable with that. But, okay, so anytime somebody talks about emission line spectra, they're going to be energy being emitted at you because electrons are falling back down. Well, the other one again talks about electrons, and absorption line spectra happens on the way up. Okay, so again, back to the flame test. Energy was absorbed by the flame. Okay, we couldn't see that part, but we could see the emission. And honestly, I'll go ahead and kind of add to this a little bit. If you're looking at the same element, these two, if you're looking at the same element, actually behave like, do you know these days with digital cameras, if I say the negative, the old-fashioned cameras used to get a negative. So basically whatever was bright on your picture was dark on the negative, whatever was dark on your picture was light on the negative. They're negatives of each other. Okay. Emission lines, sometimes you'll see me call those bright line spectra. Okay, energy is released. Okay. And then absorption line spectra, sometimes you'll see me, and you'll see why I call them bright line and dark line. Not just me, but they can be called bright line and dark line. Dark line, you're going to see that energy is absorbed. So they kind of suck a little bit of energy. All right. So this is, and the video kind of talked a little bit about this. Kind of, did you see where the video, and they were talking about how we see molecules from distant galaxies and stuff like that? And it kind of showed you like a line and kind of a dip, and then the line resumed. Okay, that's kind of what this is being shown here. And we'll see a few of these at this point in the class. But the higher up it is, okay, the intensity is greater. But the other thing, do you see, that's along the y-axis. Do you see along the x-axis we have the different types of electromagnetic radiation? The different wavelengths. Long waves, short waves. Okay. So, this could be a fingerprint from Mars. And do you buy this where this part right here are like little ticks up? Okay, ticks up in what? Ticks up in intensity. Okay, so that's why this is actually a region showing emission lines, which would be characteristic of something. There are people, and now we have computers to do it, but there are people that interpret spectra. It's a lot easier now than it used to be. But basically, they would look for signatures. Okay. Then do you see this region right here, where the intensity kind of varies, but there's no spikes? That's Kirchhoff's first law, continuous, non-interrupted. Then we go over to here, kind of getting longer wavelength, and do you see where this is kind of these are sort of discrete ticks down in intensity. Those are absorption lines. So you see where I called absorption lines dark lines? Okay, and actually emission lines are bright lines. Okay, here energy is released. Energy, capital E for energy released. And here energy is absorbed. So we have a little bit more of a tick over here. Do you see where this looks like it would have been Kirchhoff's first law, would have been continuous, kind of gently increasing intensity. But here we have some ticks down. Energy is absorbed, and you can kind of see the dark lines there. Cool. Well, just to kind of solidify it, let's look at that first one, where you can see different objects we're going to look at. A toaster, a neon lamp, a star called Spica, and the whole green leaf thing, if this works. So the first one you're going to see is kind of the energy that's coming from our sun. Okay? Yeah. Does it look like Kirchhoff's first law, kind of just continuous? There's a dude named Fraunhofer who basically took a magnifying glass and he looked really close at this and he could see absorption lines. That's kind of cool. All right, well, let's look at the toaster. Now, we're not looking at the toaster like your silver toaster. We're looking at, oh, you'll see, the toaster filament, it says. Okay, so this is just the filament of the toaster. Remember I said that we have the Roy G, well, we have the red, orange, yellow, green, blue, indigo, and violet, okay? Over here, red, where red leaves off, I said infrared picks up, and infrared is thermal energy. So honestly, you kind of see, with regard to intensity, kind of in more and more intensity, kind of in this longer wavelength. So that's the signature of the filament of a toaster. Neon lamp, I like this one too. You're like, really? I know. So what we kind of see is a blended, ooh, that's pretty. It's almost like subliminal. It's not really subliminal. But really you have these discrete colors, okay? The way a neon lamp works is neon is an element, okay? And it's a gas. So basically you fill your tube with that gas, and you go ahead and use electricity to fill your light bulb, and that electricity is supposed to excite the electrons around your neon atom, and then when they fall back down, they emit this color, these colors, okay? And we kind of see them as a... So we're going to talk about different colors of stars, but there's a very pretty star out there. It's a, well, they're all pretty, right? But there are some blue stars and some orange stars. This happens to be a blue star, kind of a hotter star. And can you see where this is opposite the toaster filament? If you kind of focus on this part over here, okay, there's the toaster, okay, and this is... Now, one of the things actually that video talked about is when you get to the shorter wavelengths, they're becoming more and more energetic. The energies are. Gamma rays, you would tell me, could really destroy some of the cells or mess with some of the nature of our cells, versus radio waves. Actually, microwaves could be a bad thing too. But this is more energetic over here. And then last but not least, we have a green leaf, where the video said that actually green is being reflected off and everything else is being absorbed, basically. So, whoops, what am I going to do? All right. So I just have kind of some examples to kind of, or to reinforce what we've been talking about. And I think I have a problem with one of my belts, but let's see. So Kirchhoff's first law, uninterrupted. Kirchhoff's first law basically says you have a source, okay, and when you go to look at all of the different wavelengths of the source, it's uninterrupted. So do you see, in order to kind of break down the different wavelengths, we're using a prism, just like Newton did. Take the light, shine it through a prism, there's nothing on the other side, except a continuous rainbow. Kirchhoff's second law says we get these, and you'll just have to bear with me, I'll draw it on here. Kirchhoff's second law says we get these emission lines. I'm going to go ahead and draw in a prism here. Okay, we can use our prism, okay, to separate out different wavelengths of color, and we will see spikes in intensities at different wavelengths depending upon what that light was passing through. So this here, you see that we have to have a cloud of gas that is oozing energy. But like this says, basically, this cloud of gas can only ooze energy because it was excited. Those electrons were somehow excited, and then they could go ahead and fall back down and give us the spectrum. They were excited by heat. So Kirchhoff's last law, his third law, says, well, on the way up, as electrons are excited, they can sucks particular energies characteristic of the electrons around the atoms. And so we get these dark line spectra. They're shown here. So notice in this case, basically, we have our source, okay, in front of our source, and it goes. We have our cloud of gas between our source and how we're going to separate the light. So this is these are created as electrons are excited on their way up. Fingerprints. So I've been kind of talking about different energy levels, and so these kind of lines that go across, these are potential energy levels. Happens to be for the simplest element, hydrogen. And hydrogen, if it's lucky, it only has one electron because it only has one proton in its center. It only has one electron to kind of jump around and make these spectral lines that you're going to see. So the NM stands for, like this says, nanometers. N is a prefix nano, and it means 1/1,000,000th of. Okay. Sorry, 1/1,000,000th of. Okay. So do you see where actually, maybe you wouldn't necessarily, but these are visible, okay, and these would be in longer, I think radio. See, it's longer nanometers, and then these shorter ones would actually be in, oh, sorry, this is be in infrared, longer, and over here, these are in ultraviolet. So just like the guy said, it depends on the jump. It's all about the jump. So for instance, kind of focusing on these possible jumps 1, 2, 3, and 4, if you want to call them that. 1, 2, 3, and 4. They release 1, 2, 3, and 4, that wavelength of energy respectively. And so what this is saying is there is that one, there is that one, there is that one, and there is that one. And depending upon how intense these energies are, how intense they are, you might see this as a flame test that gives us red if that one overpowered the other ones. So looking at the shorter wavelengths of energy, okay, that can be emitted. Notice these are bigger transitions. They're bigger steps down, more energy, and actually we couldn't see those, so they won't appear here. Okay, and over here, these are in the infrared. We wouldn't see those either. But the transitions are still there. Just because you can't see it doesn't mean it's not there. So I'm going to go back. Look at how this is emission. Okay, Kirchhoff's second law. And look real carefully because the next one is the negative of this one. Okay, so notice this is absorption. We have the characteristics 2, 1, 1, and 1. Again, for hydrogen, so the absorption is, I'm going to say mirror image, but it's a negative image of the emission. So this one kind of shows you, this is one of my favorites, so I guess I better play it. So the first thing you're going to see is continuous spectrum. Basically, you have your telescope here's your telescope, enjoying gathering light from your star. Notice that the star is white, so it's got all colors of the rainbow coming this way. So now I'm going to add a gas between the telescope and the source. So in that gas, in that cloud, basically, it is sucking in, let's see what colors are coming out. You have to look fast. Looks like
red, green.
Yeah, red, green, maybe some blue. But particular energies are being removed. What consequence does that have? Well, if you look closely, your telescope, you're going to see that spectrum from that star minus those energies. Why? Because that those electrons in those atoms in that gas are sucking that energy. So now the next thing's kind of cool. I'm going to actually relocate the telescope, and instead of being kind of looking at the source with the gas in between, I'm going to look at the gas. So I'm going to move to the side. Okay, it looks like a hydrogen, doesn't it? So moving to the side, you can't see it very well. I'm like, where are those? But moving to the side, what I see is, as the electrons fall back down, they re-emit that energy, but only at those particular colors. Okay. And so if I wait long enough, I'm going to kind of get that miscellaneous kind of random kicking out of energies at those particular wavelengths that they sucked in before. So this spectrum, there's two lines here, okay, and kind of two other lines here, is the negative of the other one I saw. Okay. I might have said it wrong. This looks like Kirchhoff's second law. Emission lines, and the other one was absorption lines. I'll go back to telescope 1. I like it. Okay, so helium, that we looked at hydrogen. That's helium, sodium. That kind of makes sense. Flame tests for sodium are that kind of orange color. Neon, actually those are going to be how the electrons around neon will either absorb energy or release energy at those colors. So we can't visit a star, and this is, sometimes students will take this class and they're like, really, how did they know that stuff? How did they know the elemental composition of a distant galaxy? And this is part of what they're doing. So I told you that Fraunhofer actually looked at what looked like a continuous spectrum, and he looked closely at the sun's spectra, and this is what the sun, okay? So these dark line spectra simply mean then, I guess there's no simple to it, but it means basically the sun is shining all forms of, the sun is trying to send us all colors of the rainbow. And there's some gas between us and the sun that is robbing those wavelengths. And as it turns out, that's kind of like the atmosphere of the sun. We can understand the atmosphere of the sun because of those lines. Okay. So just to kind of summarize, remember this is kind of a spectra, a fingerprint of something. Along the y-axis is intensity, along the x-axis is wavelength. And if we talk about regions A, B, C, D, and E, can you see where continuous spectra would be uninterrupted? So you're talking B and E. Okay. Emission spectra are where you see blips of energy. That would be A. And absorption spectra would be these two regions, the C and the D. All right. Well, one of the characteristics of stars is how hot a star is. You're like, I so am not going to visit that star and take my thermometer, okay? Yeah, that's not going to work. But one of the things we do with stars is kind of like I've been saying already, is we basically turn our telescopes to the star and we get radiation from the star and we put it on a plot, just kind of like you've been seeing. So here are 3 different stars, okay? The blue, the yellow, and the red. Okay, those are 3 different stars. So what we did for those stars was to, and it probably takes a little while, to go basically and get a snapshot for the energies that star is sending us. So for this blue star, kind of orient yourself. It's similar to the graphs we've been looking at, where along the x-axis we have wavelength. Okay, we have the cousin thing going on. So here's visible light, and then we have shorter wavelengths over here. Okay, we have longer wavelengths over here. Notice the cool thing, it kind of goes back to what that guy was saying about energies coming from all over the place. We definitely have energies in the region where our eyes aren't sensitive, and we definitely have energies in the region where our eyes are not sensitive in the long wavelength too. But the pretty blue star we see is because of this information right here. So that we can use that fingerprint, that's called black body radiation curve, okay, to know that star is about 15,000 Kelvin. The next one is our sun. Its surface, now this would all be surface temperatures, is about almost 6,000 Kelvin. Some of the pretty red stars you see up there, basically the redder the star, the cooler it is. I know it sounds backwards. Okay. So a few things, and we'll be talking about this more, but a few things. Can you see for the hotter star, for just these three examples, the hotter it is, the peak is the shorter. The peak goes this way for being hot, and that's characteristic. When I say this way, I'm going to more, shorter wavelengths, more energy. And the cooler peak is that way. Oops, sorry, cooler. The other thing is, can you see where the hotter it is, it's also intensity is raised on everything. And the cooler it is, it's more squatty. So there's one more curve here, and it's just adorable. Look at that last curve. So in general, I know that sometimes we have fevers, and sometimes we're chill or cooler. But if we were to take a snapshot, a black body radiation curve of people, isn't that adorable? This is what we look like. Okay, we ooze radiation. Now this isn't because the light's shining on us and all that. This is basically absent any light in a dark room. That's what you're. Isn't that adorable? So, and again, we know from that fingerprint how hot you are. Hot. Right. Okay. Well, that's a good place to stop, and we'll talk about the laws that basically are summarized here in these curves on Wednesday. And by golly, we will get through Chapter 5 on Wednesday. Famous last words.